Welcome to Learn with Longman. This is the second video in our series on organic reactions. If you haven't watched the first video about primary alcohol oxidation, make sure to check it out using the link here. In today's video, we're diving into secondary alcohol oxidation, teasing out and comparing oxidation within different alcohol groups. So if you're ready, hit that subscribe button and let's get started. Previously, we met the alcohol family. Primary alcohols have the hydroxyl holding carbon bonding to only one carbon buddy. Secondary alcohols have two carbon pals, and the tertiary alcohols have carbons all around, containing three carbon besties. Let's also remind ourselves of primary alcohol oxidation. We start with a primary alcohol like ethanol. We heat things up and introduce the right oxidizing agent. Then that OH group transforms, turning first into an aldehyde, and guess what? Keep that chemistry party going, and that aldehyde goes all the way to becoming a carboxylic acid. It's like a step-by-step makeover, turning into something completely new. When we kick things off with secondary alcohols, get ready for a twist. Add some heat and oxidizing agent, a bit of time, and voila, the alcohol transforms into a ketone. And this can be pretty cool, as you can get some pretty amazing ketones. Take propan-2-ol and turn it into propanone, also called acetone, and yeah, you can clean up your old nail polish. And that's not all. Ever heard of methyl oxide? Probably not, but it is the secret sauce in many perfumes. Wow. Using chemistry to make ketones leaves you feeling a little bit like a wholesome, nice-smelling Walter White. Alright, let's get into the nuts and bolts and write the redox equation happening here. Let's break it down, starting with the oxidation half equation. Write out the full structural formula of the organic reactants and products. In this case, propan-2-ol and propanone. Now we need to balance it. Easy peasy. Toss in a couple of hydrogen ions and 2 electrons as products. Now let's talk reduction. Quickly consult your data booklets. Find your oxidizing agent, in this case permanganate, and voila, piece of cake. Finally, we're merging the two halves, crafting a balanced redox reaction. Take note of the number of electrons in each half and even these out by multiplying the oxidation equation by 5 and the reduction by 2. Nail this skill, and guess what? You'll be rocking the exam with a grin from ear to ear. Let's talk tertiary alcohols, the rebels of the alcohol family. These guys, they're like the cool cousins who skip out on Christmas. You see, alcohol oxidation is all about the swanky swap of a CH bond with a CO bond, and tertiary alcohols want none of it. Why, you ask? Well, they've got a carbon without any cyclic hydrogens, so no CH swapperoo for them. Okay folks, it's game time. Welcome to Guess the Alcohol's Name. We've got butan-1-ol, butan-2-ol, and our lucky star, methyl propan-2-ol. Take a peek. Can you spot the difference? Here's the catch. You can't unless you decode the magic of an oxidation reaction. Get ready, because we're bringing in acidified potassium permanganate. And guess what? All solutions turn a fabulous shade of purple. But in one test tube, this colour quickly changes to colourless. Why? The permanganate's being reduced to the pink or slightly colourless manganese 2+ ions. That's the primary alcohol, which reacts the fastest because it's got that OH group sticking out on the end of the molecule, ready for action. Soon afterwards, another test tube waves goodbye to its colour. This is our secondary alcohol. It joined the oxidation party, but it took a bit longer because the OH group is hiding out inside the molecule. Last but not least, the final solution keeps its purple pride. The tertiary alcohol's on the scene, but it's too chill to oxidize, leaving the permanganate purple. By the way, ever heard of my Teachers Pay Teachers? Discover Learn with Longman, your go-to for top quality educational tools. Tap the link in the description for a boost to your lessons. Alongside with many other resources, this booklet covers all things organic reactions. Let's dive into an introductory question about secondary alcohol oxidation. Your task: describe the redox reaction of pentantuol and provide observations. This question is worth 5 marks, so pause the video, take a moment to reflect, and write before comparing your answer. You're back! Did you balance the redox half equation, meticulously including water, hydrogen ions, and electrons? Accurately write the redox half equation, referencing your data sheets if needed? And combine the equations, ensuring the balance of water and hydrogen. Regarding observations, remember that potassium permanganate transitions from purple to light pink during the reaction, sometimes even appearing colourless. Let's embark on a more intriguing journey, where we're tasked with differentiating between 3 alcohols: butan-1-ol, butan-2-ol, and methyl propan-2-ol. Utilising the arsenal of standard laboratory reagents, this isn't your run-of-the-mill experiment. It's a redox challenge, so have a think about what we have learned and come back for the answer. As you prepared your response, did you keep these critical elements in mind? Is the experimental setup described? Did you acidify the oxidizing agent? Did you describe the expected colour changes, which provide the identity of the alcohol, along with the timing of these colour changes? When it comes to equations, there are 2 in play, each uniquely tailored to the type of alcohol being tested. The primary, butan-1-ol, and the secondary, butan-2-ol, will yield different reactions, so precision is paramount. As we come to the end of this video, I hope you've learned a lot. Don't forget to subscribe and explore Learn with Longman on Teachers Pay Teachers for additional resources that can help you excel, whether you're a teacher or a learner. Thanks for watching.